So let's talk about the argument principle, which is a theorem for counting the number of zeros or poles of a function inside some cycle, inside some path. It can be either used for holomorphic functions just to count the zeros, or it can be used for meromorphic functions to count both zeros and poles, although it only gives us an integer really, so it gives us actually the number of zeros minus the number of poles. Now how do we want to count the zeros? We want to count them with multiplicity. So for example, the function z squared times z minus 1 cubed. Well, it's only 0 at two places, 0 and 1, but it really has 5 zeros. It has 2 zeros at 0, so it's zeros is really 0, 0, 1, 1, 1, and there's 3 zeros at 1. So really we want to count the multiplicity. If you have a zero of multiplicity 2 somewhere, you really have 2 zeros. And same with poles. We can count those as multiplicity, where the order of the pole is the multiplicity of the pole. All right. So here is the theorem. So suppose we have an open set, and we have a cycle in U that's homologous to 0 in U. That means it doesn't go around anything in the complement of U. Right? Suppose that we have a function f, which is meromorphic, so we're allowed infinity. It's meromorphic and it has no zeros or poles on gamma. And furthermore, we're gonna have that all the we write down all the zeros of f as z1 through zn, and all the poles of f p1 through pl. So we enumerate them. So there's only finitely, we're assuming just finitely many zeros, finitely many poles. Then the theorem is that we have the following formula. We have this integral of f prime over f around gamma really is sort of counting the zeros and counting the poles. What it does is basically it adds up all the winding numbers around the zero and subtracts all the winding numbers around the poles. Okay, now actually this is the term that we're going to prove, and this is quite often a useful variant of the theorem. Is if we have a holomorphic function, let's call it h, on U, and we stick it into the integral, then we have the following formula. We basically have the h in there, and then the h comes in on the right hand side, being evaluated at the zeros, and it's being evaluated at the poles, and it's really it's an arbitrary holomorphic function. All right, now this restriction about finitely many zeros and finitely many poles is not really a big deal. So normally in an open set, the number of zeros and poles is countable. It could be a large set, it could be an infinite set. It's countable, but it could be infinite. But we can assume finite. Leave this as an exercise. There is really only finitely many zeros or poles inside any gamma. That as long as the gamma is homologous to 0, then if we look at all the points around which the winding number is non-zero, then there's at most finitely many such zeros and finitely many such poles, right? So this is not a not really a restriction. We could if you have a bigger U and F maybe has infinitely many, just take a slightly smaller U, and you will have gamma is still gonna be in there, still homologous to 0, and F is just gonna have finitely many. So this is not a big deal. All right. Now the integral f prime over f around gamma, really what it does, it gives I times the change in argument of f as we traverse gamma, meaning we start at some point and we look at the argument of f at the starting point of gamma. Think of gamma just as a path right now. So we start somewhere and we look at what the argument is, and then we follow the values of f around gamma until we come back to back where we started, and the argument has changed somehow. And that's really what this counts. And why is that? Well, the antiderivative, or the quote-unquote antiderivative, because it's not a function, of f prime over f is log of f. And so you have the real part. The real part is an actual function. The real part is the modulus of f, but the imaginary part is the argument. And so if we follow a branch of the logarithm around gamma, we're gonna get how much does the argument of f change, right? Well, and times the I, because it's the imaginary part of the logarithm. And to get an integer, once around is 2 pi, so we have to divide by 2 pi I, right? Because we have to get rid of the I, and we have to get rid of the 2 pi, which is one loop around 0. Okay, now commonly the way that you set it up is that you just make the winding number around points in U either 0 or 1. Really, if you have more, then you can always modify your gamma so that you only get 1 or 0. And then you can just sort of think of the inside of gamma. That's where you have where you wind around once, right? And everything else is outside of gamma, right? And if that's true, then in the formula, right, what we did was we would sum up all the winding numbers. Well, if all the winding numbers are 1, then we just count the zeros and the poles. Well, we subtract the 2, right? So if there are n zeros and L poles, then it's n minus L is the integer that we get. And if you have, again, this is often applies to holomorphic functions, so they're just talking about the n and not the L, right? L is 0. All right, so let's look at the proof. We're going to prove the version of the theorem with the h, because the basic version without the h is easy to prove just by letting h be 1, right? If you set h be equal to 1, you get precisely that initial version of the argument principle. So it's going to be basically just an application of residue theorem. So write down the integral that we want to evaluate, and let's write it down according to the residue theorem. Now, this function h times f prime divided by f has isolated singularities. Well, wherever f had a pole, that function would have a pole, and if it had a zero, well, that function would also have a pole. So we want to figure out what all those residues are, and then we can just write down what the formula is of what the integral is using the residue term, right? And it already looks quite it's almost we're almost done, right? Basically, what we have to show is that if Zj is a zero of order k, then the residue over there should really just be k, right? Or well, h at Zj times k, right? So without the h, it should just be k. All right. So let's suppose that we are at a zero of multiplicity k, or a pole of order minus k. It's going to work the same way. And we can suppose, without loss of generality, that is the origin. Otherwise, you have to subtract it in these formulas. But so without loss of generality, let's suppose that it is the origin, so that we're basically multiplying instead of z minus zj or z minus pj, we're just writing z. And the way that we'll write it down is let f be, we're going to basically factor out z to the k. Now, if it's zero of multiplicity k, you can write down this formula, z to the k times capital F of z, where f at 0 is non-zero, right? And similarly, if it's a pole, in which case k is going to be negative, right? So so that's for f. And for h, what we do is we just pull out the value at 0, right? So basically, we pull out the constant term in its expansion. So we write h of z as h at 0 plus z times something, right? And now we write down the expression that we have, h times f prime divided by f. And well, we write it down in this, and using these formulas, and we notice that if once this is the derivative of little f, and you notice that there is a z to the k minus 1 factor in both. And so we can factor that out. So we're really left with 1 over z over here, right? And that's that 1 over z out here in the formula. And so once all the dust settles, if we move out that 1 over z, we figure out what all has 1 over z in it. It's k times h at 0, and then we have this rest of the formula, and that's now a holomorphic function, at least near 0. The only place where that could possibly be bad is at 0, and now f at 0 is it's a holomorphic function, so it's not going to have a pole, and it's non-zero at 0. So again, it doesn't have a pole. So these two terms are holomorphic at 0, right? And so we have some constant k times h 0 times 1 over z. And that's really giving us our the residue, right? So that means that the residue of h times f prime over f at 0 is k times h naught. I claim that that's good enough for the proof because well, that's exactly what I wanted it to be, right? The k has to be there because we have to count with multiplicity, right? So if it's a 0 of multiplicity k, I'd better have that k in there, right? Similarly, if it's a pole, well, then that k is in there, but then with a negative sign, and that's where this negative sign comes in, right? All right. So that's the proof. It's really just an application of the residue theorem and just direct computation of the residues. So let's talk a little bit about some application of the argument principle. Now, maybe the first and simplest application is maybe a little bit of a surprising way to do this. Is if we have, let's say, a polynomial or any holomorphic function, but it's common for polynomials. One thing that we want to do with polynomials is find their zeros, right? Find their roots, and this theorem tells us how to locate them. What we can do is we can numerically estimate this this integral over here, and we don't even have to be very precise. Just as long as we do it to basically within 1/2, within 0.5, it should be, the error should be less than that, so that we can just take the closest integer, and that's the number of zeros, right? Well, I mean, as long as, of course, this f was not 0 on gamma. If we were so unlucky that that we had we were 0 there, but if we're not, how unlucky that would be if we take some gamma and then we happen to hit a 0 of f, right? It's just a curve in the plane. Okay, so that gives us a way to basically locate zeros, right? You could think, is there a 0 in this disk? Well, you could estimate this integral by however you estimate integrals. You could just do something really simple just by computing the some Riemann sums, or you could maybe use the Simpson's rule, or however you want to. This is just a one variable integral, right? After all, this is just a calculus 1 exercise, except with complex numbers. Now, there's more that we can do with that h. So something that is done, as I think combinatorialists like this quite a bit, but this is, for example, as applications, let's say in several complex variables, is if we take if we look at the zeros of f, maybe that are inside some gamma, right? And let's just assume again, just like before, that gamma only goes once around them, right? That the winding number is exactly 1. Then what we can do is basically we can compute these power sums. So we can either find the sum of all the zeros, or the sum of the squares of all the zeros, sum of the cubes of all the zeros. And that's just done by letting h be z to the k, because once we do that, we get we get h evaluated at all those zeros, right? So, well, we get the power sum, right? So if we can somehow compute this this integral, then we can compute these power sums. Now, there's, for example, one place where this is used is that the zeros of polynomials, well, up to order, they're really continuous. They change continuously with the coefficients, and the way that's done is by looking at these kind of integrals. You can basically prove that, well, maybe the zeros themselves are not continuous, but any so-called symmetric functions of them are continuous, and it's enough to consider the power sums, right? So all the power sums of the zeros are continuous functions if we change the coefficients of polynomials continuously. Now, we could even take this further. Suppose that we have found a place where there's exactly 1 0 inside some gamma. So it's a zero. It's a simple zero. It's a zero of multiplicity 1. Well, we could just actually compute it by this formula, right? So and that's the same idea as just above, right? Except there's only 1 0, so it's just a sum of that 1 0. Okay, so that's the argument principle, and a couple of minor applications, and of course we're gonna see more applications of this. More theoretically, we're gonna get more theorems out of this.